everyone, we are Group 1 and this is our NTP project.
Hi, I'm Edwin, and this is my MTP project at NTU. I'm in charge of the Raspberry Pi software that powers our autonomous robot system. The Raspberry Pi acts as the brain of the robot. It handles high-level logic, including Bluetooth communication, camera image capture, YOLO object detection, and automation algorithms like maze solving. The RPi communicates with the STM32 controller using a serial connection, and this connection allows the RPi to send motor control commands in ASCII text, for example, to move forward. Here, the STM32 reads this command and translates them into precise motor action. We also connect a Bluetooth device to the RPi to receive user command. These are in JSON format. For example, a command like action movement direction F tells the robot to start moving forward until a stop command is received. Finally, to make the robot behavior more natural, we implemented a continuous movement using a background thread. This thread keeps sending movement packets where a send active thread is true. We can switch direction on the fly.
Hi, I'm Wilson. For the image recognition function of our robot, we use the YOLO V8 model to train an image detection system. We utilize and train over 4,000 images, including both color and black and white versions, to account for different lighting conditions during actual runs. We then split the dataset into train, test, and valid datasets. The trained model was able to accurately identify all the required symbols from our symbol list. After training, we deployed the camera onto the Raspberry Pi and tested it using the Pi's onboard camera. The model successfully detected all test symbols in real time.
Hi, I'm Yanjing and would like to introduce you our Android UI. The UI is structured into three main sections: Arena View, which maximizes to provide the clearest possible view, the Tool Panel, the Manual Panel. User can simply just drag and drop the robot, the obstacle into the arena. To shift it, just simply click and drag it. In order to assign the facing direction, just press and hold and select the corresponding direction. The Tool Panel is for the ease of executing the task and to clear out the obstacles in the arena. The Bluetooth panel will pop out to show us the paired device as well as nearby device. The Logger panel is help us for debugging purpose.
I'm Lux and I'm in charge of algorithm. This is a simulator I built to showcase the algorithm. By default, the robot starts at 1-1, but you can change the robot position as such. You can also add obstacles, like so. And there is also the reset robot and reset all button. After you added all the obstacles, when you press the submit button, there will be a request sent over to the algorithm server, who will then calculate the shortest path and send it back to the web server, which you can see by pressing the play button. There are also arrows for you to iterate through each step to see the step that the robot took. This is a showcase of the algorithm on the robot.
Hi, I'm Yizhe. I will continue to talk about how we implemented the algorithm on the RPi. We use an A-star search algorithm to find the shortest path between waypoints. To decide the best visibility order for all obstacles, we applied dynamic programming, solving a version of traveling salesman problem. And our system uses a Flask server on RPi running our path planning algorithm and sending commands to the STM32 controller. Once the full path is found, we convert it into robot commands like FW20, FR90, or snap using our command generator module. These commands are sent over serial to the STM32, which drives the motors and executes them step by step. Obstacles are input via the Android app, then sent as JSON to our server, each with position, direction, and ID.
For some reason, our autonomous detection could not work. Therefore, for the second run, we used the manual detection. For the second task using manual detection, our robot was able to detect all the symbols.